the learning objectives for this segment are going to be determining the limiting reactants in a reaction and the excess of the non-limiting reactants. So let's just think about this conceptually. I like to think about things I can visualize, like molecules as little balls, and think about what's going on there. So let's say we have some reaction. The red spheres represent element A. Which element? Who cares? Some element. The blue spheres represent element B. Which is the limiting reactant in the reaction depicted below? So we can see that we have A has A is just a single sphere, occurs at a single element. B occurs as B2, and then it reacts to form molecules of AB2. So which of the reactants are limiting? So the product is AB2. So if we look here at what's going on, which one is used up? The one that's used up is the limiting reactant. So we can see that there are no molecules of A left. A is the limiting reactant. When all the A is used up, the reaction stops. The rest of the B2 is just left over. So that is the basic concept of limiting reactants. It's whatever, the reaction occurs until one of the reactants is used up, the first reactant that's used up, and then we're done. Nothing else happens. So the concept is straightforward. It's just putting it in the stoichiometry where it starts to, you have to go through a lot of steps before you can do that. Okay, so let's work an example of this. We've got the concept, let's work an example. So 5 grams of iron is reacted with 5 grams of water according to the chemical equation shown below. So if you were completely not thinking about this at all, you could say, well, there's the same amount of iron as water. Of course, first of all, we know that things react according to the proportions of molecules, not weight. So first we have to convert it to molecules, but second, we also need to make sure it's a balanced chemical reaction, or we don't know how many iron reacts with how much water. Okay, so let's just do this with algebra. That's guarantees we'll get the right answer. So let's say that we have A, B, C, D. Probably could be done by inspection, but I just want to give you guys practice. So for algebra, we've got for iron, we've got A equals 3C, 3C not D, C is the iron oxide. For O, we have that B equals 4C, and we have for H that B equals D. So let's set why not C equals 1? If C is equal to 1, then A is equal to 3. B is 4C. Well, that's pretty straightforward. So that means B is equal to 4 since C is 1. And then B is equal to D, so D equals 4 as well. So that's an example where you could just, you don't even have to add things together. You can just do it mostly by inspection. So this is 3. Let me put in front just so we're 3, 4. B is 4. C is 1. And H is 4. Okay, great. So we've got a balanced chemical reaction now. So what is the limiting reactant in this system? So let's start doing some stoichiometry. And what I'm going to do is, we know it's going to produce hydrogen. Let's assume that iron reacts completely. How much hydrogen gas is going to be produced? So we have 5.0 grams of iron. And we can just look iron up on the periodic table. 845 grams iron and 1 mole of iron here. And so grams of iron cancels out. We get 0.0895 mole of iron. And now we want to see how much we get of hydrogen. So each 3 moles of iron reacts to produce 4 moles of H2. So we're going to be canceling that out, and we get 0.119 moles of H2. All right, so that if the iron reacts completely, that's how much H2 gas will be produced. Now let's look at the water. What if the water is in excess? How much is produced? if the water is limiting and the iron is excess, how much hydrogen would be produced in that case? So 5 grams H2O, and we won't calculate the molar mass. You know how to do it. 18.02 grams of H2O over 1 mole H2O. Grams of H2O cancel. We get 0.277 mole H2O. And now we see that 4 moles of H2O produce 4 moles of H2, and the 4's cancel. Mole H2O cancels. We get out 0.277 moles of H2. Okay, so now here's where the logic comes in. 5 grams of iron produces 0.119 mole H2. 5 grams of water, if that entirely reacted, would produce 0.277 moles of H2. So therefore, iron is the limiting reactant, because once 0.119 moles of H2 are produced, all the iron's gone. There's still water left over to react. So because the amount produced by iron is less than the amount produced by H2O, iron is limiting. That is the limiting reactant. So that's what you want to think about. Think through the logic there. Iron produces less reactant, therefore it is the limiting reactant. When it's all used up, then there's still going to be water left over. So which component is excess? Well, whatever's not limiting. So it's going to be H2O. H2O is excess. So how much is excess? Well, when there's going to be 0.119 moles of H2 produced, so 0.119 moles of H2 produced, how much water did that take? Well, it took, so 4 moles of H2, 4 moles of H2O, so 0.119 moles of H2O was used up. How much did we start with? We started with 0.277 minus 0.119, which gives us 0.158 moles H2O. That's how much H2O is still sitting around. It didn't react. So now we just multiply that by the molar mass. 1 mole of H2O, 18.02 grams of H2O, and the moles of H2O cancel out. We get 2.847 grams of H2O. That would be 2.8 grams excess H2O. Okay. So that would be the amount of excess. Let's keep thinking through this problem a little bit more. Let's go on to, let's think a little more about this problem. So how much iron oxide is produced? How much H2? Well, the amount of iron oxide that's produced is going to be limited by the limiting reagent. We know that we have 0.0895 moles of iron, and 3 moles of iron produces 1 mole of iron oxide. So that is 0.0298 moles of Fe3O4 produced. So the molar mass of iron oxide, Fe3O4, is going to be 3 times 55.845 for the iron, plus 4, 1600, 231.54 grams per mole for iron oxide. times 0.0298 grams of Fe, mole of Fe, mole of Fe, moles of Fe cancel. That gives us 6.90 grams Fe3O4. And how much hydrogen is produced? Same calculation, 0.0895 mole Fe. A little sloppy there. Mole Fe. And 3 moles Fe produces 4 moles H2. And the molar mass of H2 gas, 1 mole of H2, 2.016 grams of H2 is equal to 0.24 grams. Wow, that looks like a 3. 24 grams of H2. So let's check one more thing. Is mass conserved? So what do we have at the end of this reaction? There's no more iron, that's gone. So before we had 5.0 grams Fe plus 5.0 grams H2O, 10.0 grams. After we get 2.85 grams H2O plus 6.90 grams Fe3O4 plus 0.24 grams H2. And if you add that up, you get 9.99 grams. If you carried everything out to more significant digits, you'll get a number closer to 10 by more significant digits. But that's just because that we're rounding things and we have fewer, we only have 2 significant digits to start with. So it's not surprising that we only get something that's 10 within 3 significant digits. So mass is conserved, and it must be the case because we have the same number of atoms before as we did after. If all the atoms are conserved, then all the mass is conserved as well.